What's going on, everyone? Welcome back. Patrick here, and moving on to another trig limit. So we got the limit as x approaches 0 of sine squared mx over nx squared. So like I've done in the previous examples, I'm going to be using these results here to help me out in the process. If you didn't watch those previous examples that are listed on the site in a certain order before this one, please watch those first because a lot of concepts are going to carry over. So we got the limit as x approaches 0 of sine squared mx over nx squared. Now, just to do a quick little review, whenever we have sine squared, let's say of a variable, let's just say x for now, this is just notation for this. Both of these are the same thing. And to go further, we can just take that sine x and kind of show it that sine x squared and show with two sine x's that are multiplying by each other. Now, it doesn't necessarily have to be an x here. It could be any expression. Sine squared of any expression is sine of that expression squared, which is sine of that expression times the sine of that expression. So what I'm going to do here is I'm actually going to rewrite this numerator as sine mx times sine mx. Right? Took that sine squared mx, changed it to this. Both mean the same thing. And then in the denominator, I'm going to take this x squared and write it twice as well. And from here, what I'm going to do, I'm actually going to take this n, which is just a real number, some kind of constant, and I'm going to factor it out of this limit. So notice it's in the denominator, so when we do factor it out, it would be a 1 over n. So when we factor it out, we'll be left with these two. Let me just write it out, actually. I'm going to put this x under this sine mx. And split it up into two separate expressions, like that. And now what we can do is notice how they're both the same expression. So we can actually, no, let's just keep them separate. I was saying we could combine them, make it squared, and then use a limit law, but I'm actually just going to use that limit law where you're multiplying two expressions together. Either way would work, but I feel like this way is a little more consistent with what we've been doing. Like that. So we got these two limits now, right? We used the limit law where we're multiplying two expressions, so we kind of distributed this limit to both of these, quote unquote distributed. Now, notice that the limit as x approaches 0 sine mx over x, it's like sine mx over 1x. So notice that that ends up being like this, where this m here, that's the m, and then the n in this case is just the 1. So the answer is going to be m over n, or in this case, m over 1. So we actually know from that the answer to this limit is going to be m, and then this limit is the exact same. That's going to be m as well. Now, if you wanted to show your work a little bit more with that, we'd have the limit as x approaches 0 of sine mx over x. What we want to do is, to show our work more with this, we want to try to use this fundamental limit. So what we need to do is have this expression and the same expression in the denominator. So what we would do is multiply it by m over m. This m, I'm going to factor out. And then what would we be left with? We'd be left with sine mx over mx, like that. Right? So this m I put here, and then this m I factored out because it's just a constant. It's a real number. So now we could do a change of variable. Theta equals mx. So as x approaches 0, that means theta is approaching 0. So doing that change of variable, we'll have sine theta over theta, and this we know is equal to 1. So m times 1 equals m. So to go from here to here, here to there, it's this work right there. And now when you multiply these out, you'd have m times m, which is m squared, and then m squared times 1 over n gives us m squared over n. Sorry. So this ends up being the final answer for that limit.